Hello, professors and classmates. My name is Marvin Ruano from Belize, Central America, and today I'll be presenting a paper entitled Effect of TRIZ on the Creativity of Engineering Students. The source of this paper is from the Elsevier publication from the Journal of Thinking Skills and Creativity, published in 2016. With an impact factor of 1.333 and a site score of 1.62. First, let's take a look at the outline of my presentation. Number one is the research fundamentals or background of this paper. Number two, I'll be talking about the methodology used in this paper. Number three, the research design. Number four, the application of the methodology. Number five, the analysis of the results. And lastly, the conclusions and suggestions. Let us begin with the research fundamentals, a little background of the paper. Well, first of all, we can say that in today's world, in this modern world, we can see that there is a heavy reliance on engineering and technology. It's just like more and more heavily relying on technology as a whole and engineering. Worldwide or all around the world, we can see an increase, a rapid increase in the demand for engineers. However, on the other hand, we can our studies have shown that engineering students may not have the ability to solve problems. So we have a problem there. We have a high demand for engineers, but we're not sure if engineering students can have that ability to solve the problems. Engineering design combines creativity with innovative engineering techniques to convert new ideas into tangible forms. So the main question in this paper is, should engineering be part of all students' education, just as mathematics, science, arts, and all those fundamental subjects? Well, we can take a moment to digest this problem or this question and then see what some people might say. On one hand, some people might say yes, because engineering as a fundamental subject for students might help them uh, develop their thinking skills, create creative thinking, and that is useful for life in the future. Whereas, on the other hand, some might say, no, we don't need engineering as a fundamental subject of all students' education. Or we might have the right to choose which subjects we want to study. It doesn't have to be a fundamental, basic subject in schools. Let us look at the methodology. The methodology applied in this study is called TRIZ, which stands for Theory of Inventive Problem Solving, developed by a Russian, Altshuler, which is just a knowledge-based systematic methodology for inventive problem solving. Basically, a systematic approach to finding technical solutions, increasing the innovativeness of technical systems as well. So TRIZ definitely fosters a lot of creativity. It is mainly applied to technology and engineering problems. Every TRIZ problem related to innovative design involves one or more contradictory statements, which means when solving the problem presents or poses a contradiction in terms of trying to improve one parameter might mean that another parameter will deteriorate and vice versa. So one parameter improves, the other one deteriorates. So then we have a contradictory statement in the problem. Also, Altshuler uses 39 parameters in a matrix form to further analyze the contradictions between those parameters. And also, then some suggestions for improvement using the 40 inventive principles of creative invention to resolve those contradictions identified in the contradictions matrix with the 39 parameters. So basically, a flow chart for TRIZ would be you have a goal, you have a mission, then you identify some problems and you want to fix those problems. So before you do that, then you realize that the problem poses some contradictory statements and parameters whereby the 39 parameters of Alschuler comes in. Then you need to find possible strategies to deal with those parameters. So what you do is you construct a contradictions matrix. And after that, after you further analyze those contradictions, you determine, or the contradictions matrix might help you identify some alternatives to solve those contradictions, which are the appropriate strategies involving the 40 inventive principles or rules, and as shown in the chart. Then you have a better design, better plan, and at the end you have a module or a product. TRIZ applications relate more to industry, technology, business, and management, but very less to education. So that's why the main focus of this study was how to apply TRIZ in a different field in education, which hasn't been done before. From research, we know that there is a lack of findings or research relating to how TRIZ can affect students in terms of creative performance. That's why we posed the big question at the beginning. Should TRIZ be applied to all students' education system? Some people might agree, some people might disagree. So the aim of this study is relating to how TRIZ affects engineering students in terms of creative performance, overall creative performance, to better understand the creative process and provide suggestions to improve creative outcomes, which is creative products. The research design, well, this study was conducted throughout a 6-week educational program for using 121 freshman students from NTNU, which is National Taiwan Normal University, and the percentage of males was 64, which accounts, no, the percentage was 52.89%, which accounts to 64 male students, and the percentage of females was 47.11%, which accounts to 57 females in the experiment. All this group of 121 students was assigned into an experimental group which uses the TRIZ methodology and a control group which uses just the regular problem-solving skills that we have. And these two were the independent variables because participants were randomly, a male or female, were randomly assigned to the experimental group, again using the TRIZ methodology, and the control group using the regular or common problem-solving approach. And then we have the dependent variables, which were the creative process of throughout the experiment, and the creative products, which is the creative outcome of what they produced. So focusing on process and outcome. The study rated novelty and usefulness of the product design at different stages with scores from 1 to 5. And other tools were also, software tools were combined with TRIZ, and for example the Makova multivariate analysis of covariance to analyze the effects of TRIZ on students' creative processes and creative products. Now, moving on to the research design part 2. What is creative process? Well, creative process, it relates to creativity as the process of creating something new or useful and solving problems. It has 3 different stages. First, it's number 1 is identifying the problems. Number 2 is analyzing the problems. And number 3 is identifying and selecting and executing a strategy. What are creative products? Well, creative products are the ultimate goal of a creative performance, which is to produce a creative, an innovative, useful product. Other tools used in the process and design of this study were what includes the CPAM, which is the Creative Product Analysis Matrix, which is a tool for assessing the creative products based on 3 factors. At the end, the products were assessed on novelty, number 1, which is originality, being the first to create and design this product. Resolution, which includes logic, usefulness, appropriateness, the solvability of any problems, and number 3, elaboration and synthesis, which includes the aesthetic considerations and beauty of the results of the outcome of the product that they created. As we can see on the table, let's look at the procedures of experimental and control groups. Well, problem solving involves the 5 basic steps, which are number 1, identifying the problems. Number 2, analyzing the problems. Number 3, proposing strategies. Number 4, selecting a strategy. And number 5, executing a strategy. Let us look at the experimental group first using the TRIZ methodology. So step 1, what did they do was identify goals and tasks, required skills and resources available. Number 2, they listed problems and collected the data. Number 3, they specified contradictory statements and contradictory parameters. Number 4, is seek possible strategies. Number 5, they chose the best strategy. Number 6, they develop plans and design. And number 7, manufacture the product. Now let's go on the other side to the control group using just regular problem solving skills. Number 1, they identify goals and tasks, required skills and resources available, which is the same as the experimental group using TRIZ. Number 2, they list the problems only. And number 3, they collected data, which was combined for step 2 for the experimental group. Number 4, they determined possible solutions. Number 5, they chose the best solution according to criteria. And number 6, they develop plans and design. And number 7, manufacture. So we can see that there is a difference with steps 3 mainly. Steps 4. Steps 4 or 5. So there are some differences, but the main difference is that the experimental group using TRIZ actually needs to specify contradictory statements and contradictory parameters, and then seek some strategies to solve those contradictions, which the control group using the regular problem-solving approach did not do. Now let's move on to the application, whereby the main theme was, or the main task was designing and making module solar cars based on TRIZ. Students were asked to design a module solar car using limited power resources or sources, 2 solar panels only, and a motor. Students earned higher scores as they overcame more obstacles by demonstrating basic combining techniques needed to gear specifications available. So there's a picture. You can see the 2 motors, 2 panels, and a motor, and some obstacles that they had to overcome. So students recorded potential and actual impediments to produce the solar car. For example, a heavier structure offers the advantage of a more stable center of gravity. Okay, so you're designing a structure for the module solar car. You want to make it heavy, and that means more stable, more stability. But it also has the disadvantage of a reduced speed, because if it's heavier, then it will move slower. So we have stability versus speed. Then students identify contradictory statements and parameters. Uh, as we can see on the 39 contradictions matrix developed by Altshuler, on the top horizontally we have the deteriorating parameters, and on the left hand side vertically we have the improving parameters. So in the example previously mentioned, we have increase in weight leads to greater stability but reduces the speed. So in other words, we have weight improves, speed deteriorates. So as we move on to the vertical side, we need to deteriorate speed and improve weight. And that gives us some suggestions of inventive principles of how we can improve the design of a product. And in this case, we have number 2, number 8, number 15, and number 38. And then we move on to the 40 inventive principles or alternatives that will help us solve those contradictions. Teachers or professors selected task-appropriate examples for the 40 inventive principles of TRIZ ahead of time. So the teachers or the professors involved in the research, they already identified they gave some examples of, after you identify the inventive principles, what will you do? So they provided some examples for the students to follow and regarding to improving the contradictions. So we have number 2, number 8, number 15, and number 38. Let's look at them one by one. Number 2 says extraction, so that is the suggested inventive principle for improvement. Extraction, what does that mean? Well, an example provided by the teachers was to remove unnecessary chassis, whole or partial, into a breaker car chassis. Chassis is just the bottom frame of the car, the foundation of the bottom frame of the car. So it says remove unnecessary chassis, whole or partial. That will improve, that is extraction, removing some parts that are not needed for into a breaker car chassis. That will improve the design. Number 8 was counterweight. Okay, tumbling body, maybe there's a problem with balancing and one side on the other side of the solar module that transforms the vehicle weight into a hill climbing strength. All right, so something with balancing counterweight, you need to do that so that if you're climbing up, it won't tilt to one side or tilt to the other side and flip. Next, dynamicity, which is the wheels can travel directly over obstacles, then touch the ground and continue spinning. Okay, so something dynamic, some dynamics related to the wheels of the module solar car. It could be very dynamic, it could be changed. They can continue spinning on the ground or something like that to improve, to get over obstacles, like a 4-wheel drive that pushes through any slippery road or something like that. And number 38 was use strong oxidizers, which are not applicable in this design or in this case. The analysis of the results, the descriptives. However, TRIZ did not do well when it comes to the ability of identifying problems. Well, what does this mean? Well, the first step of TRIZ involves describing and defining problems. And most of us tend to just do this based on our personal experience and intuition. So maybe the abilities of TRIZ to find new problems and to encourage thinking outside the box need to be further reinforced through the creative thinking process. Okay, what about creative products? Now, TRIZ has a positive effect on the ability to produce creative products, as we saw from the results, except with regards to elaboration and visual aesthetics characteristics. Students in the experimental group perform outstandingly in terms of novelty and resolution, and TRIZ is very appropriate for implementation in schools. But you can see the difference in the two designs in the picture there. The TRIZ is not as beautiful and not as aesthetically pleasing as the one for the control group. So TRIZ focuses more on functionality rather than beauty and design of outer appearance and aesthetics. So it can improve in terms of that. As regards to novelty and resolution, great job. So it can be implemented in schools. Now we move on to the conclusion. Well, some of the limitations were that participants were aware that they were partaking in an experiment and that their behavior was being recorded and analyzed. So this might have some, can have some effect on the way you perform, because you know somebody's watching you or somebody's analyzing you, so you might not be able to be yourself and natural. And the results were obtained through only a single case study, which, again, we can say that's a limitation. A single case study might not provide the necessary results we need. Instructors may want to apply TRIZ to foster engineering students' ability to think and design. So yeah, it's proven that it could be applied into education. Other creative methods can be adopted prior to the application of TRIZ to help students further define problems and perform more creatively, because this is the area where TRIZ did not perform so well. So other methods can be used and combined with TRIZ to deal with the problem of identifying problems at the beginning. Instructors may also want to introduce other methods to help students enhance their skills related to elaboration and aesthetics, or something with beautifying. So TRIZ needs to be combined with other methods to enhance that aesthetics or beauty aspect of the design. And then TRIZ can dramatically increase students' ability to engage in creative processes and produce innovative products. So at the end, that is the result. That is the conclusion. But we still have other questions that come to mind, questions that arise. For example, is there a difference when TRIZ is applied to different engineering subjects or learning topics? Well, future research might give you the answer. Also, how does TRIZ, in the case of an educational application, since you're applying it in a new field, education, affect students with different learning abilities? So that could be also another future research topic. Everybody learns different. We have different students. We have students with special education. Now we have students that go to regular school. So there might be a difference in terms of applying TRIZ to students with different learning abilities or disabilities. So at the end, my comments or my insights of this paper are that overall it is a very simple and very clear application of TRIZ and the experiment. So there's no problem in the structure and the application of TRIZ. It's an application in a new field, education. The TRIZ has never been applied in education before, and that's really good. So I learned a lot from that. And the combination of methodologies, which is what I'm interested in with my professor J. Huang, which is Cheng Yi Huang, we're trying to apply TRIZ or combine it with another methodology and see if we can combine it or apply it into a new field. So I learned a lot from this paper, and I got some ideas of how to do that. But again, when it comes to like experiments, using students for experiments, and experiments need to be done. You cannot only do one experiment, you need to do many experiments so that you can increase the reliability of the research. So one case study and might not be, and might not show the actual results. Also, when it comes to using students, in this case freshman students, they might not take the experiment very seriously. So for me, that is a major limitation for this study, which needs to be taken as a credible for the credibility. It needs to be done with people who will take it very serious for more reliability and credibility purposes. So overall, I think TRIZ could be applied in the education system. It's just we need to have more research done in that area, in that field. Thank you for listening.